So we are going to look at counting processes. Widely used counting process called the Poisson processes, right? So what are Poisson processes? So you are familiar with the Poisson distribution, dealing with the discrete type of random variables. Poisson distribution is discrete. We usually look at a rate a certain event occurs, right? So here under stochastic processes, when we say Poisson processes, they will count the occurrence of an event that happened at a certain rate. Right? Say, for example, let's say number of landslides in hill country. Suppose you have specified a certain area as hill country and you want to measure the number of landslides, right? Say, for example, you know that depending on the rainy seasons and all those things and looking at the historical events, you have that landslides occur with a rate of, let's say, 2 per year, right? During 2 rainy seasons, suppose, you know for sure landslides will occur, right? 2 per year. So when we say 2 landslides per year for a certain area, we are not going to look at the timing, right? When it happens, in which month, you know, whether it is in the morning or the evening, the night, right? We are not interested about the time that it occurs, right? So time of occurrence is completely random. So you don't have information about time, right? So no information is available about time. What we only know is there will be, on average, 2 landslides per year, right? So when it happens within first one and the second one, what will be the gap? Nothing, no information about that will be available, and that is completely random, right? It's time of occurrence, it's completely random, right? Say another example. Number of accidents at, let's say, right? You know, there are usually in certain maps, there are high frequent accident occurring places, right? Usually when you travel, you see sometimes there are signs saying this is a place where an accident prone place, right? So maybe due to the bends in the road or the way of the road, the slippery or the indentation of the road, usually it is a place where accidents occur most of the time, right? So suppose you have such a place and you measure the number of accidents at that specific place, right? And suppose you know the rate accidents occur let's say with a rate of 10 per month, maybe in weeks, right? Per day, in days, maybe not practical, right? You can't say there will be an accident every day, right? Maybe weekly or maybe monthly or bi-weekly, right? So you can report that, right? But when you say 10 per month, which day of the month, those information are not available. But what you know is on average, there will be 10 accidents per month on average, right? So likewise, you can come up with situations where you count number of occurrences, right? And it has the rate involved with it, right? Not when it happens, but how frequently that it will happen, right? So those can be modeled as Poisson processes under stochastic basis, right? Can any of you give another example for this counting processes or Poisson process? By looking at this example, can any one of you can come up with a different example? Any different example? If you can think about a Poisson distribution, then you can come up with many examples. Number of tsunami yes, that's a good one. Sulochana, thanks. Number of tsunami events, let's say. Per decade is a better explanation, yes. In the world, or we can say in Asia or certain place of maybe Atlantic Ocean, Pacific Ocean, something like that, right? Just that is an example for a counting process, right? And when you said tsunami, that means the rate of occurrence of earthquakes, right? So that is also a possible example, number of earthquakes occurring in a certain area, right? So if you think about, there are certain countries in the world, frequent earthquakes happening, right? So you can think about those situations and model them as Poisson processes, right? So here again, sorry, the time of occurrence, we cannot do anything with that, right? You cannot predict when a tsunami will occur until an earthquake happens at the middle of the sea, right? So it is completely random. We don't have any control over it. So we don't know when it happened, but we can get an idea about how frequently that it will occur, right? If you think about per decade, something like that, right? Okay, so you can model these kind of situations using Poisson distribution. So you are familiar with the Poisson distributions or a Poisson random variable. We denote it like this: X follows Poisson. Poisson distribution has how many parameters? How many parameters are there for a Poisson distribution? Only one. And what do we call it? It's a rate, right? So usually use lambda, right? Binomial has 2 and p, that is the number of trials and probability of success. So likewise, Poisson has only one parameter, which is the rate, lambda, right? I hope you can remember the Poisson distribution. That is e to the negative lambda, lambda to x, divided by x factorial. Possible values of x can be 0, 1, 2, up to infinity, right? Discrete, 1, 2, 3, and so on, starting from 0, that is no event occurs, right? It can go up to infinity, right? So if x is Poisson with the parameter lambda, what are the mean and the variance? Anyone who can remember the mean and the variance of Poisson distribution? Mean is lambda, yes. Variance? That is also lambda, yes. So it's a special kind of distribution where both mean and the variance are same, right? Both are lambda. And then we know if you have x1, x2 up to xn, let's say, Poisson random variables, and these xi's are independent. Right? Suppose you have a series of independent Poisson random variables. Let's say xi follows Poisson with, let's say, lambda I. So x1 is Poisson with lambda 1, x2 Poisson with lambda 2, and so on. Right? If you have a series like of Poisson random variables which are independent, if you find the summation of this xi, what will be the distribution? Sum of independent Poisson random variables. Any idea? That will also follow Poisson distribution. And the parameter will be sum of these lambdas, right? It's lambda. So sum of independent Poisson random variables will be again a Poisson distribution. Now the parameter will be the sum of these lambdas, right? Say for example, suppose x1 follows Poisson with lambda 1 and x2 follows Poisson distribution with lambda 2, let's say 3. If you find a new random variable, let's say y, which is x1 plus x2, and this x1 and x2 are independent, then y is x1 plus x2, y will be a Poisson distribution. And let's say lambda, the new parameter that will be sum of lambda 1 and lambda 2, which is 1 plus 3, 4. Right? You can prove it if you want. You can apply these methods here, right? To the distribution and find it, right? So you can easily prove this one. Or if you want, you can use the moment generating function method and prove that when you have independent Poisson random variables, the sum will also follow Poisson distribution, right? Okay. Just to refresh your memory about these calculations and probabilities, let's do a small example. Let's say the number of patients arriving at a laboratory can be modeled using Poisson process. With lambda equals, let's say for a laboratory per hour, per hour. Say 10 per hour. Okay. So what does that mean? So these are arrivals, right? Now you can model arrivings and waitings and also getting the service, right? Any of them using Poisson processes, right? Say, for example, suppose there's a customer service center, okay? And you can count the arrivals, right? You start at, let's say, 8 a.m. to 10 a.m., right? But the number of people arrive in this facility at the door, right? So you can count it starting from 8 to 10. How many pass the entrance, right? So at 8 o'clock, one comes at 8:10, another one, 8:15, another one, 8:23 or 3. Likewise, you can count. From 8 to 10, how many will be there, right? So likewise, from 10 to 12, 12 to 2, right? So 2-hour period. So you can average, that should happen over a long time, and then you can find the average rate of arrivals, right? And then suppose this is a service center and people who arrive here, they will wait, right, to get the service. And if the service center is not occupied, they will get the service and leave. In that situation, there will be no waiting time, right? And even starting from here, starting from 8 to 10, they can count the number of customers who got the service, right? This is here you can find the number of arrivals. And then you can count the number of customers who got the service. Now, these two can be different, right? Because depending on the depending on the time the person has to stay with the customer in order to complete the service, depending on that, the number of customers they serve per 2 hours will be different than the arrivals, right? Or either it will be equal or less, right? Cannot be more than that. And then the waiting time, right? So if arrivals are very frequent and the services provide takes long time, there will be a queue, right? And they are waiting. The waiting time, that is a different thing, right? So that is the waiting time. You have the number of arrivals, number of customers who got the service, and in between there's a waiting time, right? So all these things can be actually explained using the Poisson process, right? So we'll look at the definition later, but keep in mind that this is how the process will go, okay? So the number of patients arriving at a laboratory, so forget about getting the service or waiting, they're just the arrivals, okay? Let's say 10 customers per hour. Maybe they come and get the service and go, maybe some has to wait, right? So that information we don't know. So we are thinking about the arrivals only, right? 10 per hour. Can you find the probability that there are 3 customers arriving between, let's say, 10 a.m. to 11 a.m. Right? So this is based on previous knowledge also, on average, that is lambda is the average, right? The rate is 10 per hour. Suppose if you select an hour randomly, say 10 to 11, what will be the probability that there are 3 customers? How do you find that probability? So what is your random variable x? Number of customers arrive in the lab. Right? So with the rate, you can say that x follows Poisson distribution with lambda equals 10, right? This is per hour, right? This is per hour. Now in this question, 10 to 11, it is also hour. So we are fine with that. We want to find the probability that x equals 3 customers. Nx follows Poisson distribution. You can find it very easily, e to the negative lambda, lambda 2x, x factorial. Lambda is 10, x is 3, so you get e to the negative 10, 10 to the power 3, 3 factorial. Can you find it quickly? You can use a simple calculator and do this calculation. Or if you have a Poisson distribution table, that is also okay. This is a small calculation. I'm sure you can do it using calculator. Probability, okay, I got one answer. Any other answers? I have one answer from Sulochana. Others? Anybody who has tried, please share your answers so we can check. Yes, so this is correct. 0.00756. Shini, yes, correct. Okay. So that is the probability, very small probability, right? Now try this one. Find the probability that there are two customers between 10 to 10:20 a.m. So 10 to 10:20, how many, what is the duration? 20 minutes, right? 20 minutes. Be careful, the rate is per hour. Now you have to find the probability per 20 minutes, not per hour. So the lambda equals 10 is per hour. So first thing you have to do is to recalculate the lambda per 20 minutes, because from 10 to 10:20, that's 20 minutes. So per hour is 60 minutes. So you can find the new lambda. Right? So let's say lambda star. What will be the new lambda? If 10 per hour, what will be the value per 20 minutes? That will be 3.330. Let's use 10 over 3, right? Because there will be rounding errors when you do the calculation. So why are we dividing by 3? Per hour is 60 minutes. 20 is 1/3 of that, right? 20 times 3 is 60. So the rate should be divided by 3. So that will be the new lambda. So the probability x equals 2 will be e to the negative 10 over 3. Now that's the new lambda. 10 over 3 to the power 2, 2 factorial. So you can find the probability. Okay, one answer is there. Ishini, yes, you are correct. So you have to do the finish the calculation. You can share your answers. Okay, 0.1982. Yes. Okay. So one last calculation. Find the probability that there are 3 customers between 10 to 10:20 and 7 customers between 10:20 to 11. Now you have 2 intervals. How do you do this one? Yes, how do you do this one? Now look at this. Look at these intervals. Let's say interval 1 is from 10 to 10:20. And the second interval, let's say interval 2 is from 10:20 to 10:40. These are non-overlapping intervals, right? They don't overlap. So this is the AND. So that means the intersection, right? 3 arriving at interval 1 and 7 arriving at interval 2, right? So when you have the intersection, how do you calculate the probabilities when they are independent? This is the multiplication rule for independent events. That will be probability 3 at interval 1 times 7 at interval 2, right? Because these are independent. Independent means these are two, they are not overlapping, right? So you can split it and find it using the multiplication rule for independent events. So you can find these probabilities separately. Interval 1 is 20 minutes, right? Lambda 10 per hour. So 20 minutes will be 10 over 3. We already did it. So let's calculate it. Arriving 3, right? times the next one. What is the new lambda? For 40 minutes, what will be the lambda? So 40 minutes is 2/3, right? 40 minutes is 2/3. So you have to multiply 10 by, here you have 10 by, and here it will be 2/3, right? So that will be 20/3. Yes. So you have negative 20/3 to power 7, 7 factorial. Okay. From that you can find the answer. Right? So you can try it. Which will be 0.0325. Okay, so this is just a recall on how you do the Poisson probability. Okay. Any question about these calculations? So let's move on to Poisson processes and the definition and the stochastic processes. Right, so here's the definition of the Poisson process. So we say Poisson process with the rate or the intensity lambda. Lambda should be greater than 0. Is a collection of random variables. So here's the mapping. NT from the sample space omega to N0 such that if there are 5 properties under this definition. The first one, N0 omega equals 0. That means at the very beginning, when you are starting counting the time, at that initial time, there will be nobody, right? You are starting the count starting from 0, right? And NS will be less than NT or S less than T, right? So what does that mean? You have the number of, let's say, the number of arrivals, right? So suppose you measure the number of arrivals starting from 10 to 11, you count, right? At S, let's say at S is the 10 o'clock, T is 11 o'clock, right? So you count the number at 10 o'clock, okay? You have a certain number. You started counting from, let's say, 8 a.m. So suppose at 10 o'clock there were 5 arrivals. And then when the time goes, you cannot have less than that, right? You cannot have 4 arrivals or 3 arrivals. It will be added. So from 5, it will be increments, right? 6, 7, 8, 9, and so on. So never, you cannot have go backs. Right? So therefore, always NS will be less than NT for S less than or equal to T. It can be same, the equal, right? Say there are 5 customers at 10 o'clock and nobody arrives, then at 11 o'clock, still it will be 5. That is possible. But you cannot go other way around. Okay. Then the next one. Give me a minute. Okay, the second one, for any k and any time value, let's say starting from 0, first, the initial one, the next one, t1, t2, up to tk, the increments, so you can say nti minus nti minus 1. I hope you can remember how we define intervals in the previous lesson. I going from 1 to up to k. Excuse me. Are stochastically independent. Those are independent increments, okay? The third one, the increments, these NTI, NT values, so those are the increments. The increments are stationary with, if you get this, the difference NT plus S minus NT. So within the interval S, right? That increment follows Poisson distribution with the rate will be lambda times S. So it's very similar to the calculations we did. So you have lambda, let's say per unit time or for certain measurement. And when you have certain interval, like here, this is per hour, but when you do for 20 minutes, you have to multiply lambda by the t. T here will be 1/3 of the original, right? T here will be 2/3 of the original. So you multiply lambda by that time fraction, right? So likewise, these increments will be again a Poisson process or Poisson distribution with the parameter lambda times S, right? So this value should be greater than 0. So that means here's your t value, time, and then you have t plus s. So within t to t plus s, the time interval is s, right? So that time fraction, you have to multiply lambda by that. If it is just one increment, that will be lambda times 1, which is lambda, right? So that is obvious. Then if you get the sample path, right? T growing from Wt in omega. The sample path is always right continuous. Right continuous. What does that mean? If you think about the increments, okay, one customer arriving, 2, 3, 4, 5, maybe then 3 together, so 8, 2 again, 8 plus 2, 10. Likewise, the increments will go up. Always it will be right continuous, right? So this will be going always upwards, right? Right continuous. Yeah, you cannot have the arrivals getting backwards, right? It's not possible, right? Either you stay there or it will go up. So it is always the right continuous. It goes up, and then finally the process has the Markov property. Markov property. So what is the Markov property? Can you remember the Markov property? Check the notes from the previous class. You can get it right. Right. So I'll explain how this start from the omega, how you can represent these increments and the time values, right? And also there's another thing you should remember, the standard Poisson process. Standard Poisson process means when lambda equals 1, right? Like the standard uniform is in between 0 and 1, standard normal is 0 and 1. Likewise, when lambda is 1, you get the standard Poisson process. Okay. So let's try to understand all these 5 explanations using a simple graph. Okay. So you have this omega, that is the sample space. You have this omega. And the increments are coming from this sample space, right? And then you have time values starting from 0 up to tk, right? Or it can go beyond that, okay? And then in between these, or for corresponding to these time values, you have the increments, right? The count, n, nti, nti plus 1, nti plus 2, and so on, okay? And these increments are stationary, and then it is also right continuous. So we'll see how we can represent this using a small sketch, okay? So let me draw the sample space first. Which is our omega, right? Suppose in my omega, I have these items, omega 1, omega 2, omega 3, omega 4, 5, 6, and so on, right? And then I'm going to draw my time values, okay? Starting from t equals 0. Then t1, I'm not going to write 1, 2, 3. These can be any value, right? No need to have the same gap, right? So I'll apply common set now, right? Okay. Uh, you have T3 plus Tk, okay? Right. Suppose these are my time values. So we are going to model the increments, okay? Okay, let's start with omega 1, okay? Suppose for that incident, let me color code it. Okay. The first arrival occurs somewhere between T0 and T1, let's say, right? And then no arrivals up to here, and then another arrival occurs at this place, and nobody up to here, and then another arrival occurs at this point, and it goes on like this, right? Another arrival at this one, and maybe no arrivals at all after that. Likewise, right? And let's say, so try another one. Let's say omega 2, starting from here. One arrival, and suppose no arrivals up to here, and then another arrival, likewise. Okay. Likewise, you can get the increment, so you can design. So what happens here is the first one arrived in between T0 and T1 for omega 1, and then another arrival at T1, so there will be now 2, right? So this will be the number of arrivals at 0. This will be number of arrivals at T1, This is number of arrivals at N2, T2. Number of arrivals at T3, right? So likewise, you can note it down. So this will be N T1 plus K, likewise, right? So you can see that it's always going up, right? Continuous, right? And you have the ns is always less than or equal to nt for s less than or equal to t, right? So you see that it's not going down. Okay, so this is how you can interpret a Poisson process, how this omega will happen or omega will behave, right? And then if you look at the time interval, right? Suppose this is our time interval, starting from 0, say t1, t2, t3. They don't have to be equal, right? Likewise. So suppose this is the first arrival. So t1 is the first arrival time for a certain incident, okay? And t2 is the second arrival time, and so on. And in between them, you have the waiting time, right? So 0, t1, t2, t3, 3, 4, those are the arrival times. And then in between, you have, let's say this is x1, x2, x3. These x's are waiting times, right? Or you may say, better to say inter-arrival times. Inter-arrival times, that is, so x1 is the arrival time or the time in between the initial point and the first arrival. X2 is the time in between first arrival and the second arrival. So that is called the inter-arrival time, right? So you have the timeline, the arrival times, and then in between them you have the inter-arrival time values, okay? So if you define these terms, these are random variables. Tn, let's say, is called the arrival time of the nth event. And then the x's, the random variable xi, this is called the inter-arrival time between successive events. I minus 1 and I. So then we can define this NT, right? So our NT, that is these increments, right? These NT values, that's the count, right? The Poisson process with rate equals, say lambda, right? Then you can calculate for a certain event x1, let's say x1, let x1 be the time to the first arrival, time to the first arrival, right? So you can see that time to the first arrival from the beginning point up to the first arrival, right? Time to the first arrival is, let's say x1. Then this x1 will be from 0 to, let's say t, right? So this is our x1. It will be greater than up to a point t, so you can write it as x1 greater than t. So if you want to find that probability, so what is that? If x1 is greater than t, that will be no arrivals in 0 to t. Can you see that? Right? If x1 is the time to the first arrival, and if you define a point t, and if you want to find the probability x1 is greater than t, right? x1 is greater than t means x1 happened after t, right? So that means there will be no arrival in between 0 to t, right? If x1 is, better not to write it like this, right? So if x1 is greater than t, that means x1, that in between value, the inter-arrival will be somewhere here, right? Somewhere here. x1 or the first arrival occurs somewhere here. So let's say t1. So if you define a time value t, right, if x1 is greater than t, that means nobody arrives until t, but later somewhere after that, the first arrival occurs. So the probability x1 greater than t means there will be no arrivals within the interval 0 to t. x1 is after that, right? So that probability will be e to the negative lambda t, right? Why is that? When you say no arrivals, that means the number of arrivals is 0, right? So simply use it with the Poisson distribution. Poisson is e to the negative lambda, lambda to x, x factorial. Here we are using lambda times t, right? Because of this, right? We are using lambda times t. T is the time measurement, right? So you can write this as e to the negative lambda t. Instead of just lambda, it will be lambda times t, the fraction, okay? X will be 0, 0 factorial, right? So when you have e to the power, any value to power 0, this will go to 1. 0 factorial is 1, so your answer is e to the negative lambda t. So that is how you get that the probability that no arrivals within the interval 0 to t will be e to the negative lambda t. Okay. Now is this clear how we got this no arrival probability? Right, you have the time intervals from 0 up to t1. T1 is the arrival of the first, t1 is the first arrival. And in between you have x1, and there's a value t somewhere in between 0 and t1. If nobody arrives within the interval 0 to t, that means the probability that there's nobody arriving within that interval 0 to t. So if you want to find that the probability no arrivals within that interval 0 to t, you can easily do that using the Poisson distribution, and you'll end up with e to the negative lambda t. Now, if you look at the other way around, if you take its complement, x1 less than t, what will be that? x1 less than t. So this is the CDF, right? If you get probability x less than certain value, that is how you find the cumulative distribution function, or fxt, right? So you can say px less than t means fxt. Then x1 greater than t means 1 minus fxt, right? So 1 minus fxt is what? E to the negative lambda t. We found it here, see? Probability x1 greater than t is e to the negative lambda t. But that is actually 1 minus fxt, right? So if 1 minus fxt is e to the negative lambda t, what is the cumulative density? 1 minus e to the negative lambda t. Now, is this familiar? What is this distribution? If your CDF is 1 minus e to the negative lambda t, what is the distribution of x? This is another well-known distribution. Anybody who can remember this distribution? Where your CDF is 1 minus e to the negative lambda t. You can guess if you have the Poisson and what will be the continuous counterpart of Poisson distribution. Yes, what is the continuous type of distribution that you deal with rates? No guesses? Nobody can figure it out? This is the exponential distribution. This is the CDF of exponential distribution with the parameter lambda, right? So x follows exponential with lambda. What does that mean? If increments follow the Poisson distribution with the rate lambda, right? If the increments follow Poisson distribution with rate lambda, the waiting times or interarrival times will follow exponential distribution with the parameter lambda. Okay, so you can see the connection between arrivals and increments, right? So the arrivals and increments, as I mentioned here, right? Arrivals and increments, the counts. The increments or the counts follow the Poisson process, Poisson distribution, and the interarrival time will follow exponential distribution with the rate lambda. Okay, so just to show that how you get this CDF of exponential 1 minus e to the negative lambda t. If x follows exponential distribution, what is the PDF? Lambda e to the negative lambda x greater than 0, 0 otherwise, right? So this is how you write the PDF of exponential distribution. Okay. Then how do you find the CDF? Can you find the CDF? You have to integrate this function starting from the lower bound, which is 0 up to any x. Right? So if you do that, you should get 1 minus e to the negative lambda t. That is the CDF. Right? So what do you get? Lambda e to the negative lambda x, and its antiderivative, we divide by negative lambda. Evaluate from 0 to x. So lambda will go out and negative value is here. Then you have to evaluate e to the negative lambda x from 0 to x. When x is x, you get e to the negative lambda x, minus when x is 0, you get e to the 0, which is 1. So with the negative sign, you get 1 minus e to the negative lambda x. So this one, right? So you get the same thing. So you can see that the waiting times or the interarrival times will follow the exponential distribution, right? So you can find or you can define these interarrival times. Here's the starting point, first arrival, second arrival, third arrival, fourth arrival, and so on. X1 is the first interarrival time, that is the time for the first arrival. X2 is the time from for the second arrival, starting from the first arrival. Likewise, you can get the interarrival times or waiting times, let's say. So X1, X2 are interarrival or waiting times. The counting process. and t. Okay. Do you have any questions up to here? What we covered so far? Poisson processes, increments, and interarrivals, their connection, and how we got the distribution and all. Is it fine to all of you? Okay. Now let's try to find some properties coming from this scenario. So think about two time values, s and t. Both are greater than 0. Okay. Now note that these two intervals are disjoint. So how will that happen? So you have from 0 to s, and then you have from s to s plus t. Okay, so this is s and t are like this. So s is a time value, a time point, and t is the addition, right? So if you draw it in a timeline, it will be like this. Starting from 0, you have s somewhere here, and then you have s plus t. Okay, so the interval from 0 to s, and then the interval s to s plus t. These two, you don't see any overlaps there. They are disjoint, right? So two different intervals, no overlaps at all, right? So they are disjoint intervals. So therefore, we can find this probability. Now look at this probability. Probability x2 greater than t given x1 equals s. Now look at this probability. What does that mean? How can you explain this in words? Probability x2 greater than t given x1 equals s. So if you go back to this probability x1 greater than t, what does that mean? No arrivals in the interval 0 up to t. Because x1 is the first arrival, up to the first arrival. No arrivals in 0 to t. That is the probability x1 greater than t. We have probability x2 greater than t. What does that mean? So t is somewhere here, right? T value is somewhere in this area. How do you say that? Probability, no arrivals. If x2 is greater than t means after this place, right? So no arrivals in which interval? S to s plus t. No arrivals within this interval. Given x1 equals s. Okay. Now what do you see here? You have the interval s to s plus t and x1 equals s. Are they dependent or independent? These two values, s, the interval s to s plus t. The interval s to s plus t, this interval, right? Given x1 equals s. S is here, right? S is here. What do you see there? You see independent increment here. Why? They are disjoint, they are not overlapping, right? So these are independent increments. So what does that mean? if you have independent events, the given probability, what will happen to the given information if they are independent? There's no information that you can get from the given one, right? So this is a conditional probability of x2 greater than t given x1 equals s. But if these two events are independent, the given probability, the information from the given one, it's useless. So this is like when you have this, you simply get PA if A and B are independent, right? Probability of event A given B equals probability of A itself if A and B are independent. So the given information coming from event B, it's useless because they are independent. B cannot do anything to A. The same thing happens here. So no arrivals within S and S plus T is independent from x1 equals S. Therefore, this is same as probability no arrival in the interval S to S plus T. Right? No arrival in the interval S to S plus T. So what is actually that probability? Same as this one, right? Doesn't matter whether it is from 0 to T or T1 to T2 or T2 to T3. Why? The previous increments are independent. Therefore, it will be always e to the negative lambda t. Okay? So that means x2 is also exponential with lambda, right? So you can show this for all the increments. So you can do the same for x3, x4, and so on. Always these are increments, right? So up to that point, what happened? It's not affecting the increment, right? Not affecting the count or the increments within the given interval. Okay. So therefore, if you can prove it like this for all xk, well, all the xk's, you can say that in general, the inter-arrival times xi, all of them are exponential with lambda, right? Sorry about that. Right. So what does that mean? All the inter-arrival times, you'll end up with the same distribution exponential with the rate lambda, right? So you can see that this is a very known property for exponential distributions. What do you call it? You call it the memoryless property. Memoryless property of exponential distribution. I'm sure you have heard about this. Exponential distribution is memoryless, right? We all are memoryless, right? Most of the time. So what is the meaning that exponential is memoryless? Exactly this, the thing that we explained here, right? So that means, say for a time value, if you want to find the probability x is greater than x plus a, given x greater than a, this is same as probability x greater than x plus a. Right? So this given one is useless. Okay? So that means if I explain it in a simple example, think about a motor vehicle, right? Think about a motor car or something. Suppose its lifetime, we usually lifetimes are exponential distribution, right? suppose the lifetime of this motor vehicle. That means how long it will work. Okay. Suppose it was running starting from, it was produced in 2000, right? In 2000. And today is 2023. Now it is 2023, right? So the probability that, so up to here, it has run 23 years, right? Up to now, it has run 23 years, right? And suppose you want to find the probability that it will work without any problem until 2025. That is the probability. The lifetime is greater than 2025, right? Knowing that it survived up to 2023, right? So you want to find the probability that this motor vehicle will run without any problem up to 2025. That means actually 25 years, right? Up to 25 years. Knowing that it ran properly 23 years up to now. That probability is same as just x greater than 25. What does that mean? The given probability that knowing that the vehicle worked properly for 23 years, that information is useless. Anyway, it will run more than 25 years, right? So what happened during these 23 years, for the lifetime, it is useless, right? So when we model lifetimes using exponential, whatever happened earlier, those information are gone. So that is the memoryless property. So the probability that the vehicle will run more than 25 years, knowing that it ran properly for 23 years, it's anyway the same probability that it will run 25 years, more than 25 years. So knowing that it was properly driving for 23 years, this information is useless. So whatever happened here, it will not affect the probability that anyway this vehicle will work properly for another 25 years or the rest of the 3 years and count. Rest 2 years, so 23 plus 2, 25. Okay, so that is called the memoryless property. The same thing here in increments and arrivals, right? So the probability that there will be no arrivals within the given interval, it has nothing to do with that, whatever happened in the previous arrivals, right? So you can think about it in usual scenarios also, right? Now think about that laboratory example, right? So from 10 to 11, there were 5 customers, right? So having 5 customers in the previous hour does not mean there will be again 5 customers in the next hour, right? So that's that information actually it's useless. They are not seeing each other. They are independent, right? So that's the same idea. So there will be no arrivals in the next hour. It does not depend whether there were 5 arrivals or whether there were no arrivals in the previous hour or whether there were 10 arrivals. It doesn't matter, right? So the number of arrivals in the next hour, it is independent from whatever happened in the previous hour, right? So that is how you define the Poisson process. That is the relationship between the arrival times and the inter-arrival times, right? So the increments will be Poisson distribution, then the inter-arrivals will be exponential distribution, okay? Right. Right, the next will be, I have to do a proof, okay? So I hope I can finish it. Let's try. Let's try to derive or get an idea about the distribution of arrival and waiting times. Right? So think about this continuous time setup. We have the time value t here. And think about a small interval, infinitesimal interval. So a delta value to the plus and to the negative side. Okay. So this is delta, very, very small value. So this will be t plus delta, and this will be t minus delta. Okay. So up to here, this will be t minus delta, and you have t and then t plus delta. So very small neighborhood around t. Okay. And then this interval is 0 to t minus delta. Okay. And if we define this distribution, right? Suppose this has the distribution ftk, that is the density function of tk, right? Assume that the probability of arriving more than one event, that means more than one arrival in this small interval, right? The neighborhood of t. Let's make it easier. Okay, let me have this, and so this whole interval is delta. Okay, so delta divided by 2 for both sides. Okay, let's use it like that. So it will be t minus delta over 2 and t plus delta over 2 is negligible. So that is a very, very, very small interval, right? So the probability of arriving more than one event within this small interval is negligible, right? So that interval is that much small. Now suppose the kth arrival happens in the interval this small interval, right? So there cannot be more than one, and the kth arrival happens within that interval. So how do you write that probability? Right? So if you get the probability, the kth arrival occurs within that interval. So that is the tk, right? That is the tk. Tk is the arrival of the kth event. And we think that the kth arrival happens within this interval. So that means tk should be in between t minus delta over 2 and t plus delta over 2, this small interval, right? So within this interval, the kth arrival occurs. So what is that probability? That probability will be, if you think about in increments, nt minus delta over 2 minus n naught, that should be k minus 1. Why? Because it's the kth interval, k minus 1 in the previous interval, right? So let me write this, and it's not enough. So let me write it in the next slide. Okay. So I'm writing it again. The increment and then the t plus delta over 2. This is 1. So what does that mean? So there is only one event, and that is the kth event. So the previous interval, that is from n0 to nt minus lambda 2. So this area, I hope you can see that in this area, you have the k minus 1 number of events. And the next event occurred, that is the kth event occurred within this interval. So that will be, so the increment is just 1, right? N are the increments, right? So there are k minus 1 increments in the interval from 0 to t minus lambda over 2. And there will be one increment within this interval t minus lambda over 2 and t plus lambda over 2. Okay. So again, the probability that the kth event occurring within this interval t minus lambda over 2 and t plus lambda over 2, that is same as the probability, the number of increments in the interval before to t minus lambda 2, that is from 0 to lambda 0 to t minus lambda delta, not lambda, delta over 2. Within that interval, there were k minus 1 increments and then one increment within the interval. So the left-hand side, you have the time values. The right-hand side, you have the increments, right? So you see, the left-hand side, you have the probability of the occurrence of the event, right? For t, right-hand side, it is the probability based on the increments, okay? So simply this means probability that the kth event occurring within that small interval, that is same as the probability there will be only one increment within that interval. Okay, only one increment. Earlier, there were k minus 1. Okay, and what we do is, since we are using this very small interval, so let's make this delta goes to 0 on both sides. Now what will happen? If you take the limit, okay, so what will happen to the left-hand side? You can write this probability tk within that interval as the CDF of tk at t times lambda, because lambda is the length of the interval. And the right-hand side, since you have the probability of these two events and they are independent, you can multiply those two probabilities. So the first probability, and then the next probability, these are overlapping, non-overlapping intervals, right? So you can do that. Now take the limit. You know the distribution. Increments are Poisson, right? So let's write this probability. Okay. So lambda times the t value, or the time value is, the time length is this. And the x, the number of increments is k minus 1. Okay, so that's the first probability. And then the next probability, lambda times, you have the interval is here delta and one increment, right? Oh, I forgot the e to the, sorry. So this is lambda e to the negative lambda t minus delta 2, okay? Times the next one, lambda times delta, one increment, e to the negative lambda times delta, divide by 1 factorial, that's k minus 1 factorial. Okay. Now check whether I have written it correctly. Is everything correct? First probability and second probability using Poisson distribution. So have lambda x e to the negative lambda e to the negative lambda t, or x over x. Okay. Okay. Right. when lambda goes, not lambda, I'm sorry, it's delta. Okay, always I'm switching lambda and delta. So this is all about delta, right? So when limit delta goes to 0, what will happen to this right-hand side? What will happen to the right-hand side? When delta goes to 0, this goes to 0, this goes to 0. So what will be the end value? So here you get lambda. I'll write the expression. Please double check it. It is a negative lambda t because delta over 2 goes to 0. One factorial is 1, so that's gone, but you have k minus 1 factorial is there. And what do we have from the other part? Just e to the 0 is 1. Delta goes to 0. Am I right? Let's double check. With a negative lambda t from here. This is gone. This is 1. Then is this correct? Lambda times delta. Anyway, I think I have made a mistake in this part. Can you double check it with the Poisson distribution whether I have substituted the correct way? Anyway, the answer should be this one. And this is exactly the gamma distribution. So you'll end up with the gamma distribution, right? For the kth arrival. So the arrivals follow the gamma distribution. Right? So the increments follow Poisson, the waiting times follow exponential, and the arrival times follow the gamma distribution. Okay. So this should be the answer. I think I have made a mistake when substituting the values for the Poisson. So please check this one, right? And figure out where I made the mistake. Anyway, you should end up with this one. So this is the gamma distribution. Okay. Yes, right. So some mistake somewhere in the Poisson when I substitute the values for the Poisson, right? Now you should end up with this gamma distribution. So that means T1 you have up the waiting time x1. At T2 you have waiting time up to 1 and the waiting time up to 2, x1 plus x2. So at the third arrival you have inter-arrival times up to 1, up to second arrival, up to third arrival, and likewise, right? And these xi's are independent. Yes, so this sum of these exponentials, you'll end up with the gamma distributions, right? But all the xi's are independent TIs are not independent. So remember that. Although the inter-arrival times are independent, the TIs, right? So that is the arrivals, those are not independent, right? The reason is simply this: the third arrival occurs after the second occurs after the first, and so on. They are depending on each other, right? So these are the important results that you will get from here. The first one, x1 and x2 are independent, not only 1 and 2. I'll generalize it. That means xi minus 1 and xi, they are independent. And these xi's follow exponential distribution. And if you take the kth arrival time, that will be the sum of x1 up to xk. So this tk follows gamma distribution with the parameters k and lambda. So you can check this one, the parameters k and lambda. K is the k, that k means the kth arrival, right? So if you take an example, suppose you have the increments follow Poisson with lambda 2 and xi, x1, x2 up to whatever the values be inter-arrival times. Then can you find the probability that the first arrival occurs after t equals 0.5? Think about it. Find the probability that the first arrival occurs after t equals 0.5. So the first arrival is somewhere here, after 0.5. So if the first arrival occurs somewhere here, what about this area? So you want to find first arrival, that is x1. That means the time to the first arrival, x1, is greater than 0.5. So this means the probability no arrival in the interval 0 to 0.5. Right? So this is the same way that we calculated the no arrival after first, right? Or up to the first arrival. That is e to the negative lambda t, we already derived it. So e to the negative 2 times what is t? 0.5. So that we can easily find. Okay. Another one, given that there are no arrivals before, let's say, t equals 1, find px1 greater than 3. What does that mean? You have to given, right? So you have to find the probability that the first arrival or up to the first arrival is greater than 3, given x1 greater than 1. No arrival before t minus 1, t equals 1. Now, so how do you find it? That means the probability, you can split it like this, 2 plus 1, because we have 1 here. So this is the memory loss property. So this one is useless. This is simply x1 greater than 2. right? So this is like this is from memoryless property. So what do you have? You have to find, simply find probability x1 greater than 2. E to the negative lambda t equals e to the negative 2 times t is 2. You can find the probability, right? So when you get the concept, it's very easy. You know the distributions, so you apply them and you can find the probabilities very easily, right? So if you write this in words, this means no arrivals, probability that there are no arrivals in 1 to 3, given no arrivals 0 to 1, right? So whether there are no arrivals in 0 to 1, it does not affect whether there are no arrivals from 1 to 3, right? So having no arrivals here, it's not going to affect whether there are no arrivals or arrival in the next interval. So this information is useless. So that is why this is same as probability no arrivals in 1 to 3. So 1 to 3 is t equals 3 minus 1, 2. So that is how you got this x greater than 2. Okay. This is e to the negative 2 times 2. So you have the answer, right? So easiest thing is to write down it like this. In words, no arrivals in the interval given, no arrivals in whatever the previous interval they are asking. And you can easily draw the diagram and figure out what is the time value within that. 3 minus 1 is 2. So 2 goes here. And you can find the probability using the distribution, right? So x's are exponential. This is the CDF. 1 minus of that and so on. So you can have, you can use that straight away, e to the negative lambda t, and do the calculation, right? Okay. Any questions so far? So we are not finished with the Poisson process, right? There are few theorems that we have to look at, and we'll do it next time, right? You have to look at the compound Poisson processes and theorem called superposition. So we'll do that next time. So refer this one again and try to find the mistake I did here, right? And next time, before we start the lesson, we'll do another example covering these concepts, right? So you can recall what we learned last time, and then we'll go to the rest of the Poisson processes and finish it, okay? I'll share these notes with you, so refer it and understand it, right? So we'll do another example next time. Any questions so far? Anything you have to ask before we finish the session? No questions? Or you didn't understand anything? Is it too much? The proofs and all? I don't think so. You are honest students. So, right. Okay, then we'll finish the session for today. We are not done with Poisson processes, okay? So we'll do another example next time and do the rest of the theorems and finish it. Until then, please refer to the note. Okay.